So, we continue our lecture with flush slag practice. Flush slag practice means you flush the already prepared slag from the meltdown stage, because that slag was oxidizing in nature. If we want to remove sulfur from hot metal, then an oxidizing slag is of no use. So, it has to be removed, and instead a fresh reducing slag is to be created. That is what flush slag practice means. Why it is needed? Because sulfur and phosphorus, if they are to be removed from hot metal, then because of the condition for removal of sulfur, you require a reducing slag. Therefore, one requires a flush slag practice. How it is done? Oxidizing slag of the meltdown stage is drained out, bath is deoxidized with ferrosilicon or ferromanganese, and eventually by aluminum. Having done this deoxidation process, then pulverized coke and burnt lime are added into the bath. Now, this calcium oxide reacts with carbon under the action of the arc, because arc has a very high temperature, and it produces calcium carbide plus carbon monoxide gas. Calcium carbide is a very strong desulfurizer. Now, this carbide in the slag, it reduces FeO content. That means CaC2 plus 2FeO, that is equal to calcium oxide plus iron plus 2 carbon monoxide. Now, this calcium oxide, which is again being produced, it reacts with FeS and forms CaS plus FeO, and 2FeO plus CaC2, that is equal to CaO plus 2 iron plus 2 carbon monoxide. That is how the process of desulfurization of hot metal in electric arc furnace is being done. That means, a single oxidizing slag is sufficient for removal of phosphorus. That means, if only phosphorus from hot metal is required to be removed, then a single oxidizing slag is sufficient. If sulfur and phosphorus both are to be required to be removed, then after removal of phosphorus, a reducing slag is to be created. So, that is how the refining and finishing operation is done in electric arc furnace. When this is over, then metal is tapped and cast and for further processing operation. Now, a brief comparison with basic oxygen steel making. Comparison with oxygen steel making. So, here I will put electric arc furnace, here I will put BOF, that is basic oxygen furnace. Now, say first differentiation is source of energy. In electric arc furnace, the principal source of energy is electricity, whereas in basic oxygen furnace, this chemical reactions, they supply the required amount of heat to the process, or another way you can call BOF is autogenous. No heat is supplied from outside to run basic oxygen furnace for steel making. Another, raw material. The principal raw material in electric arc furnace is scrap. Though now directly reduced iron plus hot metal, they are also used in a small proportion, but the principal source of steel production in electric arc furnace is scrap. Here in basic oxygen furnace, the principal raw material is hot metal. The principal raw material is hot metal, plus well 20-30% of the scrap is okay, but the principal raw material is hot metal. In the operating procedure, in electric arc furnace, oxygen is supplied only to remove carbon. During meltdown stage, sometimes you do require oxygen supply, but essentially you require oxygen in case of electric arc furnace when you require to remove the carbon. Whereas in basic oxygen furnace, continuous supply of oxygen, is to be carried out. In electric arc furnace, slag foaming is purposely induced. Why? In order to shield the arc so that the arc does not radiate its heat to the lining. Another objective of foaming slag is that most of the heat will be directed to heat the metal or scrap and less heat will be directed to the wall. So, the foaming slag is a part of electric arc furnace. If the slag does not foam in electric arc furnace, then conditions are created so that the slag foams. The whole objective of foaming slag is to submerge the arc so that the heat of the arc, which is very high, does not radiate to the lining of the wall. So, this is one of the main objective of foaming slag in electric arc furnace. Whereas, in basic oxygen furnace, the foaming slag does not have that objective as that of EAF. The foaming slag, it enhances the rate of carbon and phosphorus removal reaction. Another difference in the operating procedure is that of carbon injection. Carbon injection is purposely done in order to create foaming. How it is done? Because for the foaming one require a gas forming reaction, that is C plus O is equal to CO. In electric arc furnace operating with 100% scrap, hardly you have any amount of carbon which will give you carbon monoxide gas. So, for submergence of the arc in the foam, extra amount of carbon is being injected, oxygen is also injected, so that carbon monoxide evolves and the slag foams. So, what I mean to say is that for foaming slag, when the gas forming reaction is not sufficient in electric arc furnace, then it is necessary to inject carbon in the bath. So, these are some of the essential differences between basic oxygen furnace and electric arc furnace. Now, let us see the techno-economic indices. Economic indices. Say A, if you write, that is equal to 24 N M Y upon 100 T, where A is annual capacity in tons. Annual capacity in tons. N, number of working days. N is number of working days, and Y, that is equal to Y, that is yield of sound ingots, yield of sound ingots from the metallic charge, from the metallic charge, m mass of metallic charge, mass of metallic charge, and T is tape to tape time. Now, naturally, if m increases, annual capacity increases, n number of working days increases, capacity increases, and above all if tape to tape time decreases, annual capacity is also increases. Now, in fact, tape to tape time T, it depends upon some factors like say charging, how much time you take for charging, what is the time for meltdown, then how much refining is required, and whether you require oxidizing period or one requires oxidizing and reducing period. If the meltdown period is longer, naturally tape to tape time will be higher, and accordingly it will affect the annual capacity of the electric arc furnace. Now, this m, which is the mass of the metallic charge, it depends upon what steel grade is to be manufactured. It depends upon steel grade, because accordingly you have to see what proportion of scrap, DRI and so on are to be mixed, and then it will also depend upon method of teaming, because once the steel is finished, then steel is to be teamed. Now, say manufacturing cost, of a steel from electric arc furnace, cost of metallic charge, then electrical energy consumption, the kilowatt hour per ton, then electrode consumption, refractory consumption, then what are the wages. So, all these they include the cost of electric steel production. Among them, the cost of metallic charge is also very high and followed by the electrical energy. So, wherever electrical energy is cheap, the cost of steel production will also be cheap. Now, little bit about noise control and emissions. Noise control and emissions. Now, if you happen to see an electric arc furnace plant, that is a mini steel plant, and if you happen to be there during the meltdown stage, then you will understand the sound and the noise that is created by the production of the arc. That is, when the electrodes are lowered, a very large amount of sound is being produced because of the arc and so on. So, one of the most important consideration in case of electric arc furnace is to control the noise. Another, say you have say poisonous carbon monoxide, one is to take sufficient measure, then toxic NOx, because under the action of the arc, if some infiltrated air is there, then nitrogen can decompose to N and it may react with NO. So, that may form the NOx, and that is very poisonous gas. Now, in this particular case, possibly foaming slag practice will be very good, because then the arc will be submerged in the foaming slag, and whatever air which is being infiltrated into the electric arc furnace, that will not come into the contact with the arc. Around 15 to 25 kg dust is produced per ton of steel. Now, this dust contains iron oxide, manganese oxide and zinc oxide. From where the zinc is coming? Zinc is coming from the automotive scrap, because if the galvanized steels, their scrap is being used, then a large amount of zinc will also be joining the dust which is coming out of the electric arc furnace. Plus may also contain Fe2O3, which is highly oxidized state of iron, may also contain FeXO, may also contain SiO2, because all these things are generated because of the very high temperature coming in the electric arc furnace. So, having seen the operation of the electric arc furnace, this operation for carbon steel making and for alloy steel making will not be very different. The difference will be, for example, in carbon steel making you may charging either 100% scrap or 70% scrap and plus other raw material. In alloy steel scrap or in alloy steel production, you may be using only alloy steel scrap, except otherwise the operation is more or less similar. Now, having understood the operation, let us look into the developments in EAF technology. Developments in electric arc furnace technology. Now, in the last 2 decades, several developments in electric arc furnace technology took place, particularly because of the concept of mini steel plants. Most of the mini steel plants, they work with the electric arc furnace. The steel production from electric arc furnace has to be competitive with that of basic oxygen furnace. In order to make the electric arc furnace steel competitive with that of basic oxygen furnace, it has become imperative that the developments are introduced into the electric arc furnace technology, so that the cost becomes comparable to that of basic oxygen furnace. The main development that took place in order to decrease tape to tape time, to decrease tape to tape time, to decrease electrode consumption, to decrease electrode consumption, and to reduce electric power, to reduce electric power per ton of steel. These 3 factors, they constitute the cost component of the production of steel. In conventional EAF, without any development, the tape to tape time was the order of 2.5 to 3 hours. It is a too long a time, and it is not comparative with that of the basic oxygen furnace, where tape to tape time of 400 tons of steel is around an hour. Electrode consumption is also an important part of the cost of the steel that is being produced from the electric arc furnace. Electric power is the main cost for production of steel. So, concerning these 3 points, a significant development have been taken place in the last 2 decades, particularly because the mini steel plants have grown. All mini steel plants have electric arc furnaces, and just to give you a figure, already I gave you earlier, but here I think let me repeat this figure. The contribution from electric arc furnace to the total steel production, or rather total crude steel production under Indian condition in the year 2007-2008 was 26%, where in that year 7-8 India has produced 50.3 million tons of steel. So, there is a significant contribution from electric arc furnace. Till that period around 226 electric arc furnaces were there in the country. So, developments were essential, and now let me show on this particular graph I am showing the developments in electric arc furnace. The developments in EAF technology. Now, before I tell this particular graph, one thing which is very important that I should tell you is that these are all technological developments. The technological development, they are associated with the investment also. Now, that technology will diffuse into the market that has ROI, that is return on investment, is high, and as well as their payback period is very low. So, one is to look the various developments that have taken place in electric arc furnace steel making from the angle of ROI and payback period. ROI means return on investment and payback period. That development or that technological development will be accepted by the market when its payback period is low and the return on investment will be high. So, that is an important thing. So, in this particular graph, this is here kilowatt hour per ton, y axis is kilowatt hour per ton, and here is the year. On this side, this is the electrode consumption, this is the electrode consumption, say in kg per ton. Now, here the small, this I will put as 200, and this small scale is the tape to tape time, tape to tape time. Now, tape to tape time has decreased from 65 around when it was 180 minutes. Today, the electric arc furnace you can find as per the literature, it can tape even in 40 minutes. Has also continuously decreased. The electrode consumption you have to read, this is the year wise, and this side is the electrode consumption. Starting it was around 6.5 kg per ton, it has continuously decreased to a figure of 1.2 kg per ton with the successive development that took place over the years. As regards power consumption, which was here say at around 630 kilowatt hour per ton, you can imagine the huge power consumption in 60s or 70s, it has continuously decreased to a value of around 290 kilowatt hour per ton. Now, say around 70 secondary steel making have come into picture. Secondary steel making was developed, and with the introduction of secondary steel making, it has become possible that some of the refining and finishing operation could be done in the outside the electric arc furnace, and hence the power consumption will be reducing. Around 75 to this year, water cooled walls were introduced. Water cooled walls, side walls or the roof, they were introduced, and that also contributed decrease in tape to tape time, decrease in power consumption, as well as the electrode consumption also. In around 80s, scrap preheating was introduced. Scrap preheating technology was introduced. If you heat the scrap, you are introducing certain amount of energy into the furnace, naturally the power consumption will also be decreasing. In around say 90s or here somewhere here, DC electric arc furnace has been introduced. In around say 85, which I have forgotten, I have to tell you, around 85 or 85 period, the high power arc furnaces, high power arc furnaces and foamy stack practice was introduced. For your information, these years which I have shown, they are approximate, they can vary from a year or here and there, but what I wanted to emphasize over the fact, continuously development in the electric arc furnace technology made possible to decrease the power consumption, to decrease the electrode consumption and to decrease the tape to tape time, with the result refractory consumption will also decrease, because now the electric arc furnace vessel is handling liquid steel for a small amount of time. The energy balance of a modern electric arc furnace. Let us see energy balance of a modern electric arc furnace. Energy balance of a modern electric arc furnace. Now, say 60 to 65% of energy is introduced by electricity, 30 to 35% of energy is introduced by the chemical reaction. So, this side to this side, these are the energy input. On the right hand side, around 53% of energy, 53% of energy is carried by steel, because you are taping the steel at around 1600 or plus 1650. So, it will also carry a very large amount of heat. So, you are seeing 53% of the total energy input into the electric arc furnace is being carried away by the steel. Of course, you cannot do much. 17% of the heat is lost by the cooling water. That means a large amount of water circulates and you have to the panel and the walls, it takes around 17% of the total heat. 20% of the heat, 20% of heat is carried by the waste gases, is carried by waste gases. Remember, the waste gases contains carbon monoxide, as well as they are being discharged at 1400 degrees Celsius. So, what percentage of energy it is shown here, that is 20% energy is taken by the waste gases, is only the sensible heat. Remember, carbon monoxide has also potential energy. So, its combustion will also generate a large amount of energy, and 10% heat is carried by slag, carried by slag. Now, you notice from this energy energy balance diagram of a modern electric arc furnace, in the absence of any energy other than electrical energy, the electric arc furnace worked on 100% electrical energy. The developments which took place over the years, they have allowed other source of energy to be introduced into the electric arc furnace, and that has tremendously decreased the electrical energy required per ton of steel. You are looking in the energy balance diagram, around 30 to 35% energy is coming from chemical reaction. Also, the heat carried by the waste gases has attracted the attention of technologists, and they also thought why not to use this waste heat energy. So, the developments in EAF is mainly concentrated on the use of waste gases and how to supply additional amount of energy or how to supply an alternative energy in the electric arc furnace. Now, what I am going to do, I will now classify the developments in electric arc furnace. I will make a diagram for you, the developments in electric arc furnace. So, developments in electric arc furnace has taken place principally, say, one in the furnace design. Furnace design. Another development took place process technological operating devices. Third, uses of chemical energy. Uses of chemical energy. Fourth development took place in the area of charge mix. In the furnace design, two developments are to be noted. One is the use of high power transformer. High power transformer, and second is in the development of shell. In the process technological parameters, some development which took place, one is employment of bottom stirring. Foamy slag practice. And third, scrap preheating. In the uses of chemical energy, the developments went, one is oxidation reaction, say oxidation reaction, post combustion, use of oxy fuel burner, and carbon injection. For charge mix, also considerable development took place in the charge mix. Hot metal, Fe3C, and the important development is in the use of directly reduced iron, which is also called HBI, hot briquetted iron. So, this is a chart for development which took place over the years in electric arc furnace. Now, I will take one by one. Now, let us go first of all the furnace design. Transformers. Current trend is to have electric arc furnace with higher capacities and high power transformer, because the productivity of electric arc furnace, among other factors, it depends on the capacity of the transformer power. So, the current trend is to go for high power transformers. So, I will like to classify this transformer, say the low power electric arc furnace. Low power electric arc furnace, they have a transformer rated capacity varies from 100 kilovolt ampere per ton to 200 kilovolt ampere per ton. These electric arc furnaces equipped with these transformers, they are known as low power electric arc furnaces. Another, the medium power electric arc furnaces, they have the transformer capacity 200 kilovolt ampere per ton varies to 400 kilovolt ampere per ton. Now, high power EAF, high power electric arc furnace, they have from 400 kilovolt ampere per ton to as high as 700 kilovolt ampere per ton. Ultra high power electric arc furnace, they have 700 kilovolt ampere per ton and it goes up to 1000 kilovolt ampere per ton. So, these furnaces are called ultra high powered furnaces. Now, the current trend wherever it is possible is to go for ultra high power furnaces. Now, for example, if you want to have 100 ton electric arc furnace, then if this furnace is to be equipped with ultra high power transformer, then the transformer capacity should have 70 megavolt ampere or 700 kilovolt ampere per ton for ultra high power transformer capacity. Then second is about the furnace shell design. Second development took place in the area of shell design. So, I will put it now as a lower section and upper section. Lower section includes, that is, hearth plus freeboard. Upper section rest, that is side wall and roof and so on. Now, with dividing these two, it means there is a concept of split shell design, design. Now, in the split shell design, you have lower section and upper section, and they are, they are connected so that no air leaks. The only advantage of a split shell design is that at the time of repairing or at the time of refractory lining, if suppose lower section requires or upper section requires, then accordingly the time required for refractory lining is saved, because depending upon which part has gone bad, that part can be removed and that part can be refractory lined. Now, another, say, for increasing the capacity, what is being done now is the tapered wall concept is being used. Tapered wall is being adopted. In a tapered wall, say if this is the furnace wall, earlier, say if we have this sort of electric arc furnace, now the trend is, say you have a tapered wall, so that these are the new furnaces and these are the old ones. So, the whole thing is that you have made the tapered wall is dia of the hearth and lower side section of the shell are of larger diameter than the top opening. Now, the advantage of this newer design is, some advantages of new design, for example, larger side wall lining life, Now, since the distance from the electrode to the lining to the side wall of the lining has increased, so longer side wall lining life, and then on account of this you have improved thermal efficiency, improved thermal efficiency, and third of course, you have greater shell volume. You have greater shell volume because the diameter has become a little larger. So, greater shell volume, improved thermal efficiency, and the most important advantage is that the lining life could be increased because the distance between the electrode and the sidewall now is increased. Another say important development in case of shell is say design of cooling system, for roof and sidewall. That means, sidewall and the roof they have the pipes where the water flows, so that the amount of heat which goes out it decreases. Third development is new design of electrodes. New design of electrodes. Water cooled electrodes, argon injection through hollow electrode, they are all the practices they have cut down the reduction in electrode consumption. Another important development, as I have said, is the DC electric arc furnace. DC electric arc furnace. As already I have given in the introduction, the current passes from graphite electrode to the anode which is embedded in the bottom. You use only single graphite electrode, and on account of which certain advantages that are claimed for DC electric arc furnace, certain advantages which are claimed for DC electric arc furnace, you have lower electrode consumption, lower electrode consumption. Now, first of all, you have only one electrode instead of 3 that is there in the AC electric arc furnace. So, on account of which you have a lower electrode consumption, because you have only one electrode which is exposed. Second advantage is that arc power is directed to the melt. Arc power is directed to the melt, electrode is relatively cooler. Electrode is relatively cooler, relatively with reference to the AC electric arc furnace. Now, how arc power is directed to the melt when we compare to the ACEF, and ACEF generates an electric arc because scrap acts as an anode. So, the heat transfer occurs from the arc to the melt. In case of DCEF, you have one anode that is embedded at the bottom and one graphite electrode at the top. So, the current flows in the metal because of the cathode and anode. So, arc power is better directed to the melt as compared that of ACEF. Therefore, the electricity utilization is much better in case of DCEF. The only problem in case of DCEF is arrangement of anode at the bottom of the electric arc furnace, because there lies the whole technological details how the electrodes are embedded in the bottom of the anode. Say DC arc furnace, they create lower noise. Why lower noise? Because you have only now one electrode. Then arc is also more stable. Arc is also more stable. So, these are the certain advantages of DCEF, but the electrode technology limits diameter to a maximum of 700 millimeter, allowing a DC current of 100 kiloampere and power of 70 megavolt ampere for single electrode furnace, because you have only one electrode. If you want to increase the diameter of the electrode in order to increase the current, then you have to go for 1000 or 1200 millimeter electrode, but at this point of time the electrode technology does not allow to produce an electrode of larger diameter. That means with this the furnace size is limited to around 200 tons, that is the maximum size as far as the literature says. Now, another development in case of say development in process operating technologies. In process operating technologies, one is for example bottom stirring. One is bottom stirring. When you stir anything, the temperature and the concentration gradient will be eliminated, and therefore the refining reactions are faster. So, one can write down the advantages. First advantage would be elimination of gradients. Elimination of gradients. Second advantage, shortens step to step time. Shortens step to step time. Third, improvement in yield. Improvement in yield. Fourth, reduction in refractory electrode and power consumption Now, this advantage is coming because of shortening of tape to tape time. When you shorten the tape to tape time, naturally the electrodes are exposed for a lesser amount of time. The one particular heat is exposed also for a short time with the refractory, and hence all these things will follow. Another important advantage for bottom stirring, it helps dissolution of large pieces of scrap. Large pieces of scrap, because now the stirring conditions are good. So, the scrap can be dissolved little bit faster. Now, very important thing that comes where these bottom stirring plugs are being introduced. For stirring purposes, one uses the inert gas like argon or nitrogen. If the steel can accept nitrogen, then nitrogen is stirring. If the steel cannot accept nitrogen, then argon is stirring. Now, common sense says if you have 3 electrodes, then the position of 3 electrodes with respect to bath is clear. Then the stirring plug should be put in between the electrodes. Now, another important thing, the development of bottom plugs. Now, these bottom plugs, they look of this particular way. Say these are the schematic representation of 2 types of bottom plugs. Schematic presentation of bottom plugs. Now, remember, the stirring of the gas through the bottom of the converter, it does not involve any science, it requires a technology. One has to design the plug so that it can inject argon or nitrogen through the bottom of the electric arc furnace continuously, uninterruptedly, and without plugging. Where is the science here? Here it involves purely a technological issue. I could get 2 designs of the plug from the literature, but there could be many more. You may think of some other design, because ultimately it has to work at place. Now, in one design, This is the refractory lining, this is the refractory, and this is the porous plug. Here you put argon or nitrogen. These are the gas bubbles. This is slag, and naturally these are the bubbles that are going out. So, here the stirring plug is a sort of a very straight pipes. I mean this stirring plug has to be designed and has to be made. In this particular case, which I will put as A, what you are doing, that stirring plug is directly in contact with the melt. So, this is the melt. Stirring plug is directly in contact with the melt. What does it mean? You have to blow continuously and constantly certain amount of gas, so that the bottom plug does not plug. If they plug it, no gas will flow and the advantage of bottom stirring will not be there. In another design, this is again the porous plug. From here argon or nitrogen, this is the refractory lining, these are the gas bubbles, this is the melt, this is the slag, and these are the say bubbles. Now, what has been done in this design? The refractory plug is shorter and the distance between the bottom of the melt and the plug is rammed by a porous refractory mass, rammed by porous refractory mass. So, in fact, this thing which is being shown over here, this is a porous refractory mass. So, what happens in this particular design? The porous plug does not have contact with the melt. The refractory mass of the hearth, it is in contact with the melt. Of course, the design of the porous refractory mass is an important feature here, because now how the gas will flow? Now, the gas will flow through the plug, through the porous refractory, and then ultimately to the melt. So, here a larger surface area of the melt will be covered as compared to in the design A. So, if I put this is design B, so here I mean little more area, because everywhere the gas will come, and so a little larger area will be covered by the injection of the gas as compared to that of the A design. So, this A, if it is called direct plug, the B is called indirect plug. B is called indirect plug. The difference between the two, which is a very important difference, in A type of design, the plug is directly in contact with the melt. So, you can imagine the operational difficulties that could be there. A continuous amount of gas has to be injected through the plug, otherwise the melt will penetrate and the some of the holes of the plug will be blocked, and then it has to go for repair. In the design B, which is an indirect plug, no doubt the plug is not directly in contact with the melt. Melt is in contact with the porous refractory, that is between the bottom of the melt and the top of the plug. A porous refractory mass is rammed, gas is injected through the plug, it discharges through the refractory through the porous refractory mass and is injected into the melt. Obviously, advantages of the indirect type of plug is a large surface area of the bath will be covered, the stirring will be better, but then one has to also design, fabricate and manufacture the porous refractory mass, so that it allows the gas injection. So, these are the one of the say important differences between the two type of flux. However, there could be another designs also. So, further developments in electric arc furnace will be covered in the next lecture. Thank you.